Good day everyone, welcome back to my channel. Today we are looking at the distance formula. Now, the distance formula is one of those formulas in mathematics which are of great importance when it comes to Euclidean geometry. And it's very important that one becomes accustomed to these formulas because one needs to actually be able to apply them successfully whenever you actually work with distances in mathematics. Now, for us to be able to understand the logic behind distance formulas, it's very important to actually look at the Cartesian plane. So we have our Cartesian plane. Suppose that we have the distance on our y-axis. So we have distance in kilometers. We also have the distance in kilometers on our x-axis. Okay, and then we have our y-axis and also have our x-axis. Next thing that I like to highlight is also to look at our variable, or rather the axis itself, which is our y-axis. It's a vertical axis in this case. And we also have our x-axis, which is the horizontal axis. I've posted a video regarding the axis, so at the stage it's very important that one is already familiar with this annotation or analysis moving forward. Okay, so we need to consider other avenues with regards to our Cartesian plane. In this case, we're looking at the x-axis, and notice that our x-axis is actually graduated, and you have markings rather on it, and then you also have our y-axis, so it's got markings going from 0 to infinity, but we'll just simply stop at a certain point. In this case, let's first start with the x-axis. We start at 0 and count in denominations of 20. So we have 20, we have 40, we have 60, we have 80, we have 100. We'll just simply stop at 120. That's now our x-axis. Similarly, with the y-axis start at 0, we have 20. We count in denominations 20 as well. So we have 40, 60, we just stop at 80 for reference purposes. So another very critical point of great significance to this application is to identify that, or take note that we actually have a river course. So we have a river starting at 0 when x is 0, y is also 0, so in other words at our origin. So we have P at that point at the origin, and we also have on the other side we have Q. That's now the end point of this river course. Okay, so now to be able to identify certain conditions with regards to this, I'll actually have to amplify a very important narration. Is to note that at P we have our coordinates. So we have our x coordinate. Remember, we have x and y. Our coordinate system works in x and y. So we start with x first. So at P, or the origin, x in this case is 0, and then y is also at 0. So we have x and y at P being 0 and 0, and then at Q, x is appears to be halfway between 80 and 100, which appears to be 90. So that's our x, Okay, this is the point here. Okay, the yellow dot, and then y in this case is at 60. So now, given these parameters, it's very important to be able to fashion them out so that we're able to use them in our calculation, so you can be able to find the distance, rather than to find the approximate length of this section. Now notice we talk about approximate length, so it's not necessarily the actual length when it comes to derivatives, of which I'll actually explain later on when you look at some other dimensions of pre-calculus and calculus. So now, to look at this, or rather calculate the distance, we're going to actually rely on our distance formula, and it goes like this. D, standing for distance, is equals to the square root of, okay, x2 minus x1, close bracket, raised to the second power, plus, open bracket, y2 minus y1, close bracket, raised to the second power. Now that's very important that one gets accustomed to this formula, because that's our distance formula. Now moving forward, remember now we need to find the approximate length of this section, or this river section, or this course. So now we have d for distance, we are squaring, okay, so we need to plug in these parameters in our formula. So at P, I'll start with P. So P, where x at P is 0, minus, and x at Q is simply 90. Close bracket, raised to the second power, plus. Remember, that's the original identity of the formula, the distance formula. So you have to maintain that plus operation. So now our y at P is also 0, minus, and our y at Q rather is actually 60. So close bracket, also raised to the second power. Okay, so we have d for distance is equals to the square root of, okay, so 0 minus 90 gives us negative 90, close bracket, raised to the second power, plus, okay, open bracket, 0 minus 60 gives us negative 60, close bracket, raised to the second power. D for distance is equals to, so now we need to be very careful here. Remember, now we are actually raising these values, and they are negative, we're raising to the second power. So anything that is any negative value raised to the second power will always yield a positive answer. So negative 90, close bracket, raised to the second power gives us 8,100. Okay, because negative times negative essentially gives us positive. Okay, so now we have 60 this time, we have negative 60, close bracket, raised to the second power, so we have 3,600. Okay. D for distance is equals to, so we have 8,100 plus 3,600, that gives us, remember this is under the square root sign, so that gives us 11,700. Okay. So D, still maintain D as distance, square root, right, we are squaring now, that's 11,700. So when you square 11,700, we get, remember we are squaring 11,700. Okay, the distance now is equals to 108,17. Okay, now that is the distance from P. In other words, the distance now, therefore, the distance P from P to Q is equals to 108.17 kilometers. Okay, and then that brings us to the end of this section on the distance formula. Thank you.